presented is going to deviate from the book. Right, the first part of chapter 8 talks about balancing chemical reactions, like just observing chemical changes. When we balance chemical equations, like this here, we can only change the coefficients in front. Normally one's not shown, coefficients is here. Once is taken. We never change the subscript, because if we change the subscript here, it can change the formula. So let's say I needed 2 sodiums, I'd never write Na sub 2 here, I just write the 2. So let's look at some problems here. This one is just a little long. So balance the equation for the reaction of solid phosphorus pentachloride with liquid water. All right, so first off, we got to get the formula for phosphorus pentachloride. What is the formula for phosphorus pentachloride? PCl5. It's solid, so we'll write a little S there. And then it's reacting with liquid water. Well, liquid water is just H2O, liquid. H2O could be solid, liquid, gas. Yielding. So yielding just means, okay, those are the reactants, what we call the reactants, yields the products. So yielding aqueous solutions of phosphoric acid. So when we think about phosphoric acid, it's an acid. So it's the ic acid. When we have ic acid, then the anine's 8, so phosphorate. But phosphorate, there's no phosphorate, so it's got to be phosphate. Phosphate's the anion for that. So what's the formula for phosphate? PO4. Yeah, PO4 3 minus. Because we know silicate. What's silicate? With the silicon. Si what? Silicate's what anchors the inner block, Here, maybe it's hard to see the periodic table up there. Let me bring up another periodic table. Here. And the reason I'm asking, why am I asking about silicate? Because this is how we figure out phosphate. We figure out very quickly what phosphate is. Right? Immediately I see it's in the 3 oxygen or the 4 oxygen. It's in the 4 oxygen, so phosphate's PO4. And the charge, I get it immediately from knowing that silicate is SiO4 4 minus, so this has got to be 3 minus, this has got to be 3 minus. So PO4 3 minus. So silicate SiO4 4 minus, we know that one. So phosphate is that. Therefore, phosphoric acid is just a phosphate ion with what cation? Acids have what cation? Hydrogen. So how many H pluses will I need to balance out? 3. So phosphoric acid has got to be H3PO4. H3PO4. And it's an aqueous solutions. Aqueous solutions, we write the AQ on there. And hydrochloric acid. Okay, hydro, when we see hydro, ic. Hydro-ic means the anion must be what? If I see hydro-ic versus phosphoric, this is just the ic acid. Ic acid means the anion was the 8, so this is going to be phosphate, phosphoric acid, phosphate. Hydroic means the anion must be, if I have a hydroic acid, the anion's got to be not 8. We only have 2 more choices. It's either ite or ite. Which one is it? It's I. So I. The anion's going to be I, so it's going to be chloride. It's going to be chloride Cl minus. So how many H pluses do I need for that? Just one. One H plus. So hydrochloric acid would be HCl. This is an example of what kind of reaction is this? This is an example of what we call a acid-base reaction. This is not an example of what we were looking at before. What was the reaction type we were looking at before? The reaction type we were looking at before was called a redox. What did redox stand for? Yeah, reduction, oxidation, or oxidation, reduction. In oxidation-reduction reactions, there's an oxidizer. What do oxidizers do? They lose electrons, oxidizers, or they take electrons? They take electrons. Reducers lose electrons. Can you name some reducers for me? Manganese is a reducer. And this is the advantage of, the advantage of the repetition is eventually the repetition gets tiring and you start to look for new things and new connections. And one of the connections that you can make is that not just manganese, but all metals, reducers. Oxidizers, name some oxidizers for me. Oxygen. Oxygen is the prototypical oxidizer. In fact, that's why they call it oxidation, because of oxygen. We live. If you're a geology major, then you know the atmosphere of the Earth, say, it's changed. Sometimes it's a reducing environment. Sometimes it's an oxidizing environment. Right now, we're in an oxidizing atmosphere. But I think in the geological history of the Earth, they're saying that there are periods of time when the atmosphere was less oxidizing, more reducing. But anyway, we have the oxidizers like oxygen. Oxygen likes to take how many electrons? Do you know how many electrons oxygen likes? 2, each oxygen. Well, anyway, going back to this, that's going to change the charge. As things gain or lose electrons, the charges change. The charge that we look at is not the charge on the overall ion. So, for example, this is the charge on the overall ion, which is, what is the charge on the overall ion? And here, in this case, it's 3 minus. What we look at is the charge on the individual atoms. The charge on the individual atoms is given a name. Do you know what that name is? The name is called the oxidation state. The oxidation state is what we look at. Like, for example, the charge on the individual hydrogen atoms, the oxidation state would be +1. Then we break it atom by atom. So, for example, if we're looking at phosphate, we have 1 phosphorus and how many oxygens? 4 oxygens. Each of those oxygens likes to be what charge? What charge does oxygen like to be? 2 minus. And it usually gets it because oxygen is pretty strong. That means what is phosphorus? +5. And so what we say is that the oxidation state of phosphorus is +5, or Roman numeral. I've been using Roman numeral 5. That's the oxidation state. 5. Over here, we could do the same thing. When we look at PCl5, there's no charge. This thing is neutral because this is a binary molecular compound. But if we pretend that it forms ions, this is just, it doesn't really, it's not an ionic compound. So, the reason we're doing the charges this way is because this gives us insight into redox chemistry. This is just one of the tools we use to analyze it. We pretend that this is ionic. If this were ionic, what would it be? What would chlorine be? What would the charge on chlorine be? Because phosphorus is variable charge. Right? It could be -3, it could be plus. But what would chlorine be? Chlorine's variable charge, but which one wants electrons more? Phosphorus or chlorine? You know which element wants electrons the most on the periodic table? You know what the most powerful oxidizer is on the periodic table? Would you say oxygen is? No, it turns out oxygen is not the most powerful. It is fluorine. The further right you go here, these ones don't want, these are not oxidizers. Neon, argon, these are unreactive. But basically, the fluorine is the most powerful. So the further you go left here, less and less powerful. Like, for example, carbon. Is carbon a powerful oxidizer? Like graphite? No. Nor is nitrogen. And so, like chlorine, yeah, it's variable charge, but chlorine, if it had a choice, it would gain how many electrons would chlorine gain? 1. We have that. That means phosphorus is what? 5. So when we look at this, did anything change for phosphorus in going from PCl5 to phosphoric acid for the phosphorus itself? Did the phosphorus gain or lose any charge? No, because it started off at +5 on the reactant side, the left side, and it ends up at +5 on the product side. We do the same thing here. We look at, I'm going to write more stuff down here, so maybe I'll write it over here. If we look at water, water is 2 hydrogens and an oxygen. Now what we're going to do is we're going to pretend that these waters consist of the ions. It isn't. It's not an ionic compound. It's what we call a molecular compound. It doesn't form an ionic lattice like we typically see for ionic compound. But we'll pretend if these were ions, what would the charges be? For example, what would the charge on oxygen be? -. Yeah, which will say 2 minus. And then the hydrogens? Plus. That'd be it. Now, we have one more, which is the HCl. HCl is borderline ionic. But we have a hydrogen and chlorine. The chlorine would be minus, and the hydrogen would be plus. Now let's take a look at the hydrogens on the left. Actually, let's go to the chlorine. If we look at the chlorines, what's the charge on chlorine here? Minus. And then we go over to HCl. What's the charge on chlorine here? Minus. And then we go to water. What's the charge on hydrogen here? Plus. Then we go to phosphoric acid. What's the charge on hydrogen and phosphoric acid? And in hydrochloric acid? So no change in charge. And then we go to oxygen. What's the charge on oxygen? It's -2 on the left. What's the charge on oxygen on the right? -2. Do you see there's no change in the oxidation state? If there's no change in the oxidation state, this is not a redox reaction. This is something we call an acid base. This is a specific type of acid base. It's a Lewis acid base type reaction. It's kind of a complex reaction. But our job is just to balance this reaction. when we balance the reaction, we just try to balance the atoms, you know. And so here I have one phosphorus. Over there I have one phosphorus. Here I have 5 chlorines. Over there I have 1 chlorine. So how can I change that? Should I put a 5 here? HCl5? No. I'm going to put a 5 out here. HCl is going to be aqueous. The water. Okay, so I got that. Okay, now what do I have to balance? Hydrogens I'll leave for later. Let's balance out the oxygens. Over here I have 1 oxygen. How many oxygens do I have here? 4. So what I'll do is I'll throw a 4 in here. When I throw a 4 in here, hopefully the hydrogens balance out. Let's take a look. That's 8, and then this 3 plus 5 is 8. And so this is what we call balanced. Here. With the atoms. You know, there are different techniques you can use. This is basically what we did. All right, let's, this balancing, sometimes, you know, sometimes we balance by atoms, sometimes we can balance by ions. You know? So in this case, we did balancing by individual atoms. But there are certain types of reactions in which the ions don't change, they just rearrange the partner. So for example, a cation and an anion will switch. And so let me give you an example of that. Let's do one more. Okay, example of balance by ions instead of atoms. And so I'm going to take something like ammonium chloride plus silver nitrate. What is silver nitrate's formula? AgNO3. Now silver is, what's the charge on silver? +1. Nitrate is a -1. So this is good. Ammonium chloride, silver nitrate. These are aqueous solutions. And when I mix these together, I'm going to form ammonium nitrate and silver chloride. And so what's the formula for ammonium nitrate? NH4, NO3, and then silver chloride is AgCl. AgCl turns out to be a solid. Ammonium nitrate is aqueous. And so this is what we call a precipitation reaction. Precipitation reaction, we starting off with liquid aqueous solutions. Then we're forming a solid. So this is a precipitation. Precipitate PPT. It's a white precipitate. Now here, you know, the easiest is not to balance by individual atoms, but to balance by ion. And so how many ammonium ions do I have on the left? 1 ammonium ion. How many ammonium ions do I have on the right? 1. How many chloride ions do I have? 1. And how many on the right? 1. How many silver ions? 1. 1. And how many nitrates? 1 and 1. And so here, if we balance by ions, then it's easier than balancing by atoms. Because if we balance by atoms, you know, how many nitrogen atoms do I have on the left? 2, you know? And so it becomes more complex. This is a very simple example. But this is a different kind of reaction. This is not redox because all the ions, you know, they're just rearranged. I still have ammoniums, I still have chlorides, I still have silver ions and nitrate ions. So none of the charges have changed. But this is not an acid-base reaction. This is not a redox. This is another type of reaction. We call this type of reaction the metathesis reaction. And this specific metathesis goes by the name double replacement. We're going to look at these in more detail later. talk about it right now. So we have different ways of interpreting chemical reactions like that. We could do it at the particle level, that is individual molecules or chemical units, or we could do it at the moles. So at the particulate level, they're talking 2 hydrogen molecules plus an oxygen molecule yields 2 molecules of water. At the mole level, we can have it like this. If you look at this, for example, we could have a mole of hydrogen plus a half mole of oxygen yields a mole of water. But we wouldn't use fractions. We could use fractions if we're dealing with mole quantities. You could have a half a mole. But could you have a half a molecule? No. We don't have half molecules. So we don't use fractions for particulate level, but we can use fractions for mole level. Now, why would we use a fraction? We use a fraction because sometimes what we want to do is we want to produce a mole of water. If I want to produce 1 mole of water, how much of this stuff do I need? Versus 2 moles of water. Sometimes it's easier to think in terms of per mole. How much do you need per mole of water? So that's why we'd have fractions there. Fractions are quite common as you get. But fractions also sometimes are a little bit more of a headache. All right, so this is at the particulate level. See the reaction here. This formation of water. Now, this reaction is, do the oxidation states change in this reaction? So we have hydrogen atoms here. What are the charges on each hydrogen? Plus, so this is +1, this is +1, so the whole thing is +2. +1 + 1 equals +2. So each hydrogen is a 2+. And we have 2 of these, so it's altogether 4 positive charges, is that correct? So it's H2 with a 2+. Then we have an H+ and an H+ combined to make an H2 2+. Is that correct? Well, actually, there's no charge on this. On the H2 molecule is neutral. There's 0 charge. The only way that H2 is 0 charge is if each H atom is 0. It's 0, 0, and then we can form H2 gas. It's not an ion, it's a molecule. And so actually the charge on each hydrogen is 0. 0, 0, 0, 0. That means it has 1 proton, 1 electron for each hydrogen. It's not sure. Whereas over here, what's the charge on hydrogen? Plus. Because oxygen is, if this is -2, then this has got to be plus, plus. Plus, +2, -2, 0. H2O molecule is neutral. And so what we're doing is we're going from 0, so let's pick 1 hydrogen. If we pick 1 hydrogen, we go from 0 to plus. If we go from 0 to plus, what just happened? It just lost an electron. Let's look at oxygen. Each oxygen in this molecule it's got to be neutral. It's got to be 0 plus 0 gives me 0 because O2 doesn't have a charge. It's a neutral molecule. And so we went from 0 to, just pick one of the oxygens. If we pick one of the oxygens, we went from 0 to -2. And so what just happened? It gained 2 electrons. And so if this oxygen gains 2 electrons, this oxygen gains 2 electrons, we gain a total of 4 electrons. Therefore, we must lose a total of 4 electrons here. So we need 4 of these H's because each one loses 1 electron. So this is how it's balanced. If there's a charge change, we call it what type of reaction? Redox. This is a redox reaction. Do you know what the oxidizer is in this reaction? Oxygen and the reducer. The oxidizer takes the electrons, the reducer loses the electrons. So hydrogen is the reducer, oxygen is the oxidizer. This is a redox reaction. but we got to balance it out. Well, they already balanced it for us. This one we wouldn't balance by ions, we just balance by atoms. And so it's already balanced. Here, we don't use dozens, but if we did, this would be 2 dozen hydrogens, 1 dozen oxygen, 2 dozen water. What the chemical equation does is it just tells us the ratio. It tells us the molecule atom ratio, how they react. It tells us the mole ratio. So rather than, we don't use dozens because it's still too small. We got to use moles. So this would be 2 moles of hydrogen plus 1 mole of oxygen. 2 moles of hydrogen contains how many hydrogen molecules? 1 mole of oxygen contains how many oxygen molecules? So if dozen's way too small of a number. So if I had a mole, how many oxygen molecules are in a mole? Avogadro's number is worth. Do you know what Avogadro's number is? 6.022 times 10 to the 23rd. It's a number you have to memorize for this class. 6.022 times 10 to the 23rd. And so there'd be 6.022 times 10 to the 23rd oxygen molecules per mole. So cross that out, let's write a mole. In fact, we won't write anything because that's what we'll take it as, 1 mole. And then we're going to have 2 moles of hydrogen, which would be 12.044 times 10 to the 23rd molecule. And then we're going to make 2 moles of water, which is going to be 12.044 times 10 to the 23rd water molecules. That would be a lot of molecules. Okay, classifying the reaction type is not so easy yet because you just don't have much practice. Classifying the reaction type requires a lot of practice, a lot of examples. And so step 1, we'll just do the best we can do. In fact, I'm just going to tell you the reaction type. You know how many different types of reactions there are? If you think about all the chemical reactions that happen on Earth here, how many different types? Is it trillions of different types of reactions occurring? Maybe more, maybe less. Just in your body alone, how many different chemical reactions are occurring? You eat food, you digest it, you get energy, right? A lot of different chemical reactions occurring. And so maybe innumerable, too many to count. What do you think? But if they're innumerable, then you have to observe each one by one, studying, Like for example, how many plants and how many animals are there? How many plants and animals on this planet? A lot, right? And so what you do is you start classifying them and trying to categorize them based on certain common features. Otherwise it's too much. Otherwise you have to study each one individually. Right? And so what we'll do here is we're going to categorize them into different categories. So your book has, your book's not comprehensive, but it has maybe about 7 different categories of chemical reactions. And still it's not comprehensive, so I don't like that. So what we're going to do is we're going to have a little different way of defining the categories of reaction. And I'm going to tell you there are 3 basic types of chemical reactions. Do you know what the 3 basic types of chemical reactions are? Combustion, I'm not going to call it combustion. Combustion fits into redox. So for example, I'll tell you. This here is a combustion reaction. What we're doing is we're just burning the hydrogen. Burn the hydrogen, it can explode, obviously, or it can erupt in a huge flame, fireball. This way you're going to get a huge fireball in this reaction. This is a combustion reaction, but what we're going to do is we're going to classify it as not a single replacement reaction either. Single replacement is another type. this is why your book is getting a little too narrow. What we need to do is we need to step back and take a little broader look. This type of reaction is called a redox reaction. Redox reaction means that the oxidation states change. And so in redox, there are different subcategories of redox. One subcategory of redox is combustion, another is single replacement. There are others as well. But we don't want to get into the little subcategories. We just want the broad general classification. So redox would be one, of which there are different types of redox reactions. Let's see. Tell me the other two. Acid base, and one more, metathesis. Those are the three basic types of reactions that we're going to see. So we're just going to try to classify all the reactions that we encounter into redox, acid base, or metathesis. Okay, so this first reaction is redox reaction.
All right, step two, writing and balancing chemical equations, write a qualitative description of the reaction. We don't need to get this detailed,
Let's just skip this slide here. Your book, I told you, has many different categories, but these categories I don't like. So for example, they have combination reaction. We just saw a combination reaction. Did you see that combination reaction? It's hydrogen plus oxygen yields H2O. That's a redox combination reaction. We also have acid-base combination reactions, and we have metathesis combination reactions. So I don't really like this subcategory. But this would be an example of, let's say, an element plus element combination. That's what they're probably talking about. It's element plus element. We have a reducer and an oxidizer. Okay? Like oxygen and hydrogen. Or actually, it doesn't quite work for oxygen and hydrogen because we make H2O. This would be like sodium and fluorine. Write the equation for the combination of solid aluminum with gaseous oxygen to form a solid aluminum oxide. All right, this is a redox reaction here because aluminum, is metal. Metals tend to lose electrons. Metals are reducers. Oxygen is a great oxidizer. And so let's go ahead and write it down. Solid aluminum. What's the formula for that? A symbol. Al. That's solid. What's the charge? 3+. However, we have to be careful because are they talking about aluminum ion or aluminum metal? They're talking about aluminum metal. So what is the charge on aluminum metal? It's 0. We're going to have lattice of aluminum atoms. In fact, let's take a look and see if we can see what lattice looks like for aluminum. This is called a metallic lattice. These are architectural lattices here. To avoid this, we call it crystal lattice. Crystal lattice. You get it? There's some examples of crystal lattices for some metals. Like aluminum, nickel, silver, copper, gold have this type of lattice structure. Titanium, zinc, magnesium, cadmium have this type of lattice. Iron, vanadium, niobium, chromium have this type of lattice structure. So this is lattice. Now, if we look at all the aluminums, if these were all 3+, what would the total charge on this would be? Well, it would be 3+, 3+, 3+, 3+, 3+. We got 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 times 3.
is that the charge on that little tiny crystal? No. Each aluminum is neutral. It's got to be neutral because it's aluminum salt. Now, aluminum ion occurs too, but aluminum ion's different. You know, aluminum ion occurs in compounds. This is the element aluminum. Gaseous oxygen. What's the formula for oxygen? O2. Is there a charge? No, this is the element oxygen. In fact, all elements have zero charge in elemental form. Now, if they're in a compound, it's a different story, but this is not in a compound. Aluminum and oxygen are not in compounds, they're just alone. And oxygen is gas. To form solid aluminum oxide, now we got a compound. If we got a compound, it's aluminum oxide. So we got to figure out what the formula for aluminum oxide is. So what we do is we first figure out what's the charge on aluminum in compounds. And oxide in compounds? 2 minus. So how many aluminums, how many oxides do we need? 2 aluminums and 3 oxides will do it. And so this gives us a total positive charge of 6 plus, total negative charge of 6 minus. So we get Al2O3, and that's going to be solid. And we got solid aluminum oxide. Now we got to balance this. All right, like the previous example where it balanced by ions, you know, these are all monatomic, so we're just going to balance by atoms. So how many aluminums do I need? I need 2 aluminums. And then how many oxygens do I need? Well, I got 3 oxygens here, but I have 2 oxygens here. So this is the trick we do. The trick we do is we multiply by 3 halves. So 3 halves times 2 gives me 3. Now I have a choice. I could leave the fraction or I could get rid of the fraction. In Chem 1A, you'll leave the fraction. Oftentimes you'll leave the fraction in there because we're interested in how much you need to form 1 mole of aluminum oxide, not 2 moles. In Chem 4, when we're doing the stoichiometry, and also in Chem 1A when we do the stoichiometry, sometimes we don't like fractions. To get rid of the fractions, I'm going to multiply everything by 2. If I multiply everything by 2, that gives me 4 aluminum solids plus how many oxygens? 3 O2 gas yields 2 Al2O3 solids. And so what we should do is double check to make sure we have it balanced. 4 aluminums, 2 times 2 is 4 aluminums. 6 oxygens is 3 times 2 is 6 oxygens, 2 times 3 is 6 oxygens. So we got 4 aluminums and 6 oxygens total, and therefore it's what we can say is balanced.
So the acid can be either or, right? Like, you know how the oxygens, there's only 3 of them, and the second one is 6 of them?
Well, here, you mean this one?
Yeah.
Well, we have to do this. What this means is we got 3 O2s, and so what that is we'll have 1 O2. Actually, I'll just write it out. O2, O2, O2. That's what we mean by 3 O2s. 3 O2s has how many total oxygen atoms? 6. And then over here we have 2 of these, and each of these has 3 oxides. And so we got 2 of them, so all together we're going to have 6 oxides. And so each O2 is oxygen with what charge? 0 charge. And so take a look at what happens here. I have 6 oxygens on the left, each with what charge? 0. And then I have 6 oxygens on the right, each with what charge? 2 minus. So each oxygen must have gained how many electrons? Plus 2 electrons. plus 2 electrons, and then times 6 is a gain of a total of 12 electrons. Total were gained. Where did those 12 electrons come from? Those 12 electrons must have come from each aluminum losing how many? Each aluminum goes from aluminum 0 to what? So we have 4 aluminums at 0. And this is going to go to 4 aluminums at what charge?
Those 3.
Yeah. And so that means that each aluminum must have lost how many electrons? Minus 3 electrons. But we have 4 of them. So 4 times minus 3 is minus 12. So we lost a total of 12 electrons, and we gained a total of 12 electrons. So 12 electrons were lost, 12 electrons were gained. This is what we call, what type of reaction is this? Redox reaction. Redox. This is a redox reaction. Oops, this is the balanced redox reaction. What was the oxidizer? Oxygen, and the reducer? Aluminum. Yeah, oxygen is oxidizer, metals are typically reducers. This is a redox combination reaction, but the reason I don't like to use this combination term is because there are other combination reactions as well. So this would be an example of a combination. When we have silver ions and a chloride ion come together, if a silver ion and a chloride ion come together, we can form the compound silver chloride, which is a precipitate. And so if we have aqueous silver ions and aqueous chloride ions, they combine. Is this a redox reaction? Would you call this a combination reaction? Is this a combination reaction? Yeah, we're combining this and form this. This is a combination reaction, but this is not redox. How do I know this is not redox? The charges didn't change. So if you have a combination reaction, then automatically you got to go, what type of combination? This happens to be a metathesis combination reaction. We also have acid-base combination reactions. We'll give you an example of an acid-base combination. We have an H plus and a acetate. When an H plus and an acetate combine, do you know what forms? What forms is acetic acid. This is what we call an acid-base combination reaction. This one's Bronsted type. Bronsted. And then we have something like this. Do you recognize this, NH3? What's the name of NH3? Ammonium or ammonia? Ammonia. And then this one. Do you know what this is called? BCl3. Boron trichloride. Boron trichloride. When these this forms this compound here, just NH3PCl3. This is another combination. This is an acid-base combination, but it's Lewis. So all these are combination reactions. So I don't like that. This is why I don't like the categorization, because the categorization is you don't want so many different types of combination reactions. So what your book does is it just looks at these and ignores those. It doesn't call those combination reactions. It calls those something else. And so what we're doing is we're looking for patterns. And so all redox reactions have something in common. All acid-base reactions have something in common, and all metathesis reactions have something in common. But do all combination reactions have something in common? Well, they do in the sense that they're just combining, A and B, but they don't in other respects. And so they're missing another common link. The only one is this one, which is too simplistic. So I'm not going to dwell on their book's categorization scheme. Except this one. This is another redox. Water decomposes into its elements when electrical energy is added. So water is decomposed into the elements. So water is decomposed. Decompose just means it reacts some way to form something else into its elements. So what are the elements that make up water? There are two, hydrogen and oxygen. So hydrogen would have the formula of what? H2 and oxygen? O2. And so this is just the reverse reaction of what we just saw, where the hydrogen was combusted with the oxygen. So this is the reverse. We'll take the water and decompose it back into hydrogen and oxygen. So we need to balance this. So how many hydrogens do I have? 2. How many oxygens? 1. So there's two things I can do. I'll just do a 1/2 here. Because if I have 1 oxygen here, I'll take half an O2, that gives me 1 oxygen. And then what I can do is, if I want to get rid of the fraction, I can multiply by, in this case, what would I multiply by? 2. And so I'll have 2 waters, 2 hydrogens, and 1 oxygen. Both of these are acceptable here. But sometimes it's a hassle working with fractions. So going one way, we call this decomposition. Going the other way, we call it combination. So it's actually the reverse. This is the reverse of the previous reaction we looked at. So some reactions are reversible. That's why they write these two. Do you see the arrow? You can go forward or it can go backwards, depends. Usually when we have a reversible reaction, one way happens without any external input. The other doesn't. Like this one. If you had a cup of water on the counter, are you worried it's going to decompose? You better drink it quickly before the water decomposes. No, you aren't worried because this is going to require what they said is electrical energy. It just is not going to happen. Whereas if you had a balloon of hydrogen and oxygen, then you better be worried it's going to react. And so this is this reversible thing. The reaction can go one way or the other. Not with equal ease. Sometimes it's with equal ease. These are single replacement reactions. Single replacement reactions are what we call redox, oxidation, reduction. But the previous reactions we just looked at, these are redox reactions here too. But let's just do some balancing here. We're going to look at classifying the reactions a little later. But copper reacts with a solution of silver nitrate. Write an equation for the reaction. Copper reacts with a solution of silver nitrate. Okay, let's skip that for right now. Then we have double replacement. Double replacements are also called metathesis reactions, but they have different subcategories. For example, they have the precipitation. So your book focuses on precipitation, and then acid-base neutralization, and some others. So we'll be looking at the neutralization. be looking at this. These are the summary here, but this is not comprehensive. And there are more yet. And so what I'm going to do with this is I'm going to skip those for right now. And then let's look at chapter 9. Chapter 9 is chemical change. What was chapter 8? What's the title for chapter 8?
Chemical reaction.
What's the difference between chemical reaction and chemical change? The same thing. So this is the chemical reactions part 2. Except, the difference here is we're going to be looking at a lot of aqueous solutions. Typically when we react these things, we don't, sometimes you can react solids. You take one solid, mix it with another solid. But solid-solid reactions are slow, usually. And so we're going to look at aqueous. Aqueous reactions, you dissolve the species, like what we're doing in lab. Take a squirt of this, a squirt of that, and see how it reacts, right? There's an aqueous solution. So we're going to talk about aqueous reactions as well as gaseous reactions, as well as solid gas and solid aqueous and all combinations. But first, let's take a look at aqueous solutions in general. And when we think about, like, say for example, when copper 2 sulfate dissolves in water, we get a blue solution. What's inside that blue solution? And so the first thing is, if I have something dissolved in water, what are the species dissolved in water? So let's take a look at copper 2 sulfate. When this one, the solid, gets dissolved in water, we form copper 2 sulfate, AQ. Okay, so copper 2 sulfate, is that a molecular compound? Does it form molecules? No. It forms an ionic lattice. So what happened to the ionic lattice? Well, basically, this is what's going to happen. I shouldn't do. Let's do something simpler. Copper 2 chloride. Copper 2 chloride is similar. It forms a blue solution. So if I take the lattice of copper 2 chloride, solid, and dissolve it in water, what happens? Well, the lattice gets torn apart, basically. It gets torn apart. You see this white is copper 2, the blue is chloride. Usually cations are smaller than anions. And so here we have the copper 2, here we have the chloride. So we got copper 2 ions and chloride ions dissolved in water. The lattice gets torn apart and we form a solution of ions. And so these are called copper 2 aqueous ions and chloride aqueous ions. So we get a solution of ions. That doesn't happen for everything. So for example, if I try to dissolve ethanol in water, this ethanol for one is not lattice. Ethanol is a molecular compound. Do the molecules get torn apart? It turns out if I take ethanol and dissolve it in water, the molecules don't. The molecules stay intact. You see that? Nothing happened to the molecules. I just got dissolved molecules. Pure ethanol is liquid. So if I take pure ethanol like this and mix it with water, then the molecules just intermingle with one another. I got water molecules, I got ethanol, and now they're just mixed together. Whereas here, the copper 2 chloride gets torn apart. That lattice is no more, and it dissolves in the water. There are things that, like a hybrid kind of thing, like for example, acetic acid. If I take acetic acid, which is a molecule on the top, some of the acetic acid molecules get torn apart. When we say get torn apart, that process is called ionization. They break up into ions. And so some of the acetic acid molecules break up into hydrogen ions and acetate ions. Acetic acid consists of acetate. So here, hydrogen ions and acetate. And so if we look at this, you see this acetic acid is fine. Actually, no, it's not. This one's missing a hydrogen. And so this is acetate here. There's a hydrogen ion there. This acetic acid is intact. You see the two reds here? Look at the two reds here. This red is hydrogen. And so the hydrogen broke off this oxygen here, and now it's over here. That's what we call ionization. So the acid was ionized. Whereas this acid molecule was not ionized. nor was this. In fact, most of these are not ionized, just this one got ionized. And so this is what we call partial, it gets partially broken apart. How can we tell? How we can tell is this, charge, mobile charged species can conduct electricity. And so we can tell by the light bulb test here. So for example here, these are all mobile species, but the problem with this is there's mobility, but there's no charge. If there's no charge, we get no electrical conduction. So what we have here are two wires that are stuck in here. These two wires are called electrodes. And basically, we got to connect the wires, but there's nothing to connect the wires. We're just dipping it in there. Here, this is going to be deionized water and ethanol. If we put tap water in there, does tap water conduct electricity? Would you want to put two hot wires in there for tap water? No, they say, yeah. Like for example, you wouldn't want to, if you have a bath, let's say, you wouldn't want any electrical appliances near the bath that might fall in, right? Because water can conduct electricity. Why does water conduct electricity? Because it would have charged species in there, like this. If we put a salt, like copper 2 chloride in here, then we're going to get these charged species, which are called aqueous ions. Now these charged species can conduct electricity. Take a look at what happens now. What's happening here is that electricity is being conducted from this probe, electrode, to this one. So we got transfer of charge, which is electricity. These aren't electrons. Normally when we think about a wire, we think of electrons, but in this case, these are ions transporting the charge. Here, so we're going to get brightly lit light bulb like that. This one here, since the concentration of ions is less, we don't get as brightly lit. So we could have a lot of molecules, and most of these molecules stay as neutral molecules fine, and then a few break apart, and we're just going to get a little bit of electrical conduction. So here we're going to get high electrical conductivity. Here we get some kind of intermediate electrical conductivity, and here we get no electrical conductivity. And so we get different names for this. This is called a strong electrolyte. Strong electrolytes conduct electricity very well. This is called weak electrolyte. Weak electrolytes conduct electricity weakly. And this is what we call a non-electrolyte. Non-electrolytes don't conduct. Non-electrolytes are insulators, let's say. They don't conduct electricity very well. So I'm going to stop.